Okay guys, so we're going to talk about the properties of limits. So for the following properties, we're going to assume that A, B, and C are going to be real numbers, and all of these limits exist. So if I talk about, for instance, limit x goes to A of f of x, that's we're going to assume exists. Same with limit as x goes to A of g of x. All right, so for the first property is that the limit as x goes to A of x is going to be equal to A. And if we think about the graph of f of x equals x, this makes total sense, right? Because this graph is just, this graph looks like this. And so if I'm approaching x equals A, my output is going to be at A. And so the limit as x goes to A is going to be A. And then we have that the limit as x goes to A of b is equal to b. Well, this would be a constant function. So this would be like if I have this function right at a height of b, then anywhere that x is going towards, I can pick any a. My output is going to be b, and so my output is going towards b. Okay, so those are basically our two basic ones. Limit as x goes to A of x is going to be A, and limit as x goes to A of any constant function is equal to that constant function. All right, the second one is that if I have the limit as x goes to A of a composition of two functions, then, now also keep in mind I said that this is if the limit as x goes to A of f and the limit as x goes to A of g, if those are existing, so we don't have any issues there. Then I can pull the limit into the function composition. So I have limit as x goes to A of f of g of x is equal to f of limit as x goes to A of g of x. And this is so long as f of whatever that number ends up being inside, so long as that exists. So, for example, I have limit as x goes to 3 of the square root of x plus 6. Well, this is going to be equal to the square root of limit as x goes to 3 of x plus 6. And if I plug in 3 to x plus 6, I get 3 plus 6 gives me 9, so I get the square root of the stuff on the inside is 9, and that gives me 3. Okay? Similarly, in the beginning, if you would have just plugged in 3 from the get-go, you would get square root of 9 gives you 3. But really what you're doing is you're passing the limit in when you do that mental math. All right, then this next one, we have, if I have a linear combination of two functions, what I mean by that is I have some scalar multiple, some real number times each of these functions, and I'm adding them together. Then I can go ahead and distribute my limit across the sum. So notice that I separated these two. And I can also pull out the scalar multiples or the coefficients out in front. So instead of limit as x goes to A of b times f of x plus c times g of x, I have b times limit as x goes to A of f of x plus c times limit as x goes to A of g of x. Now we have our quotient and product. So if I have the limit of a quotient, I can write that as the quotient of the limits. So long as, again, remember in the beginning I said that these limits have to exist. So we're assuming that those limits actually do exist. And additionally, we need that the limit as x goes to A of g of x is non-zero, because otherwise we'd be dividing by 0. And then the product is very similar. I have the limit of the product of functions. And so long as each of the limits of the individual functions exist, I can write that as the product of the limits. Okay, so I have two examples. So the first one is evaluate the limit as x goes to 2 of x plus 3 squared minus sine of x minus 2. So we're going to go ahead and basically pass in this limit into these different functions. So I've got that this is going to be equal to limit as x goes to 2 of x plus limit as x goes to 2 of 3 squared minus sine of limit as x goes to 2 of x minus limit as x goes to 2 of 2. And then I go ahead and calculate each of these. And after this section, you won't need to write this out every single time, but I want you to keep in mind that you are using these limit laws anytime that you just plug in a value for a limit and evaluate it. So for this first one, limit as x goes to 2 of x is going to be 2. That's our first property. Plus, I have the limit as x goes to 2 of a constant function, so that's going to be equal to my constant function. That's, again, my first property. And then squared. And then I have minus sine of limit as x goes to 2 of x gives me 2 minus, that gives me a 2. And then I can evaluate. I have 2 plus 3 squared, which is a 5 squared, minus sine of 0. 5 squared gives me 25, and sine of 0 is equal to 0. So my final answer for this one would be 25. Okay, so for this next example, we're evaluating the limit as x goes to 1 of x squared plus x minus 2 divided by x squared minus 1. Now, if you try to just plug in 1 from the get-go, you'll notice that you run across an issue. And it's that in the denominator, when you plug in 1, you end up getting 0. And so you're trying to evaluate some number divided by 0, and it's not working. Well, if you remember from pre-calculus, whenever we had a ratio of polynomials or a rational function, in the denominator, anytime we had a 0, we had like one of two things going on. Either we had a vertical asymptote, or we had a whole. And so basically, with this function, if we have a vertical asymptote at 1, if we have a vertical asymptote at 1, we'll either have infinity, negative infinity, or does not exist for our limit. But if we have a whole, then that x value would be removed from the domain, the one that gives you 0 in the denominator, but we would still have a limit. So we need to do some algebraic manipulation to see which of these cases we have. So I'm going to go ahead and write x squared plus x minus 2 and divide by x squared minus 1. And I'm going to go ahead and factor the numerator and denominator. In the numerator, I get x plus 2, x minus 1. And in the denominator, we have difference of squares, so that gives us x plus 1, x minus 1. And so we end up getting some cancellation. These x minus 1s cancel, and we end up that this is equal to x plus 2 divided by x plus 1 anytime x is not equal to 1. When x is equal to 1, we'll be at that whole, and it will be undefined. So when we're looking at the limit as x goes to 1 of x squared plus x minus 2 over x squared minus 1, since the limit isn't actually looking at the exact function value and we're looking around the function value, since our limit is looking at what's happening around x equals 1 and not exactly at x equals 1, we can make the substitution that this is equal to the limit as x goes to 1 of x plus 2 over x plus 1, and now we can plug in x equals 1. So we got in the numerator 1 plus 2 gives us 3, in the denominator 1 plus 1 gives us 2, and so this is going to be our limit.